Good morning everyone. Today we have to discuss about basis and dimension of a vector space. I am Mrs.N.Akila, Assistant Professor, Department of Mathematics, the Standard Fireworks Rajarathinam College for Women, Sivagasi. The learning objective of this video content is to know about basis of V, dimension of V, and then some properties and example for a basis of V. First of all, we discuss about the definition of a basis. Let V be a vector space. A linearly independent spanning set of V is called a basis of V. For that, suppose S is a subset of V, then every vector of a vector space V can be uniquely represented as a linear combination of vectors V1, V2, etc. Vk. That is, V equal to R1 V1 plus R2 V2 plus etc. Rk Vk. Here V1, V2, Vk are distinct vectors from S, and R1, R2, etc. Rk are distinct real numbers from a real number system. Next we pass on to example for a standard basis. Let us consider R power n. There are n bases are available. The first entry is E1 is n tuple elements 1 0 0 0 and E2 is 0 1 0 0 and last En is all entries are 0, the last with 1. Therefore, E1, E2, etc. En span the whole space R power n and it is a linearly independent set. The next example is a set of all 2 by 2 matrices whose bases are E1, E2, etc. E4, where E1 is a 2 by 2 matrix which is of the form 1 0 0 0, that is A11 entry is only 1, balance are 0, and for second basis E2 there is second entry, that is A12 is 1, balance are 0. For E3 the third entry, that is A21 is 1 and balance are 0, and for E4 the last entry, that is A22 is 1, balance are 0. Therefore, these E1 to E4 form a basis for M22 of R. Next we discuss about the set of all polynomials of degree less than n, and its bases are 1, x, etc. up to x power n minus 1. Their linear combination forms a polynomial in R, that is a0 plus a1 x plus a2 x square plus etc. a n minus 1 x power n minus 1, where each ai belongs to R. Next we pass on to a space of all polynomials. Therefore, its bases are 1 x, x square etc. up to x power n. Next we pass on to some theorems on basis. For R power n, let us consider k vectors v1, v2, etc. vk. For this vectors, if k is less than n, they are not spanning the whole space R power n. This is our first theorem 1. If k is less than n, the vectors v1, v2, etc. vk don't span R power n. For theorem 2, if k is greater than n, then the vectors v1, v2, vk are not linearly independent. They are not linearly independent. Therefore, they are called as a linearly dependent set. And for third theorem tells this, if k is equal to n, they are both linearly independent set and it's a spanning set. Therefore, v1, v2, etc. v can become a basis for R power n. The next example tells us for R power 3, that is R cross R, they are given 4 vectors. V1 is a triplet 1 minus 1 1, V2 is a triplet 1 0 0, V3 is a triplet 1 1 1, and last V4 is a triplet 1 2 4. For this, first we take V1 and V2. They are linearly independent set, but they are not spanning the whole space R cube. Suppose if you add this to V3, then V1, V2, V3 are linearly independent set, that is their determinant is value is 2, which is not equal to 0, and they span the whole space R cube. Suppose if you add fourth vector v4, then they are become linearly independent. If we add fourth vectors v1, v2, etc. v4, they are become a linearly dependent set, but they span the whole R cube. Therefore, If n is equal to 3, then vectors v1, v2, v3 become a basis for R cube. Next we pass on to the dimension of a vector space. The first theorem 1 tells us any vector space has a basis. And theorem 2 tells us if a vector space V has a finite basis, then all its bases are finite and they have the same number of elements. This is the most important theorem that tells us for any vector space, the number of bases is not unique. Therefore, more than one bases are available for a vector space, but the number of elements in each and every bases are unique. That number represents the dimension of a vector space. For this, let us take dimension of V is the number of elements of any basis. Definition of dimension of vector spaces is the number of elements in any basis. Next we pass on to the example for the dimension of a vector space. For R power n, the dimension is n. For set of all 2 by 2 real valued matrices, the dimension is 4. That is, dimension of m of 2 comma 2 of R is equal to 4. Therefore, m cross n matrices, the dimension of m cross n of over R is equal to m by n. And next one is, if you consider the set of all polynomials of degree less than n, the dimension is equal to n. Suppose if we consider the space of all polynomials, then the dimension is infinity. Next we discuss about the dimension of the plane x plus 2 z equal to 0 in R cube. For this, let us consider the equation x plus 2 z equal to 0. Here we put z equal to s, then x is equal to minus 2s, and here y is arbitrary, then we put y is equal to t. Therefore, the triplet x comma y comma z equal to a triplet minus 2s comma t comma s, that is equal to t of 0 1 0 plus s of minus 2 0 1. Therefore, the whole space is spanned by only two vectors v1, that is 0 1 0, and v2, that is minus 2 0 1. These two vectors are linearly independent. Therefore, the dimension of the plane x plus 2 z equal to 0 in R cube is only 2. Next we have to consider the theorem to find the basis. Let S be a subset of a vector space, then the following conditions are equivalent. The first condition is S is linearly independent spanning set of V, then it is a basis. And second is S is a minimal spanning set of V, and third is S is a maximal linear independent set of V. Next we pass on to the theorem to tell about the basis. Let us consider S be a subset of a vector space, then the following conditions are equivalent. The first condition is S is a linearly independent spanning set of V, that is it is a basis, and second one is S is a minimal spanning set of V, that is minimal spanning set represent if you remove any element from S, then it cannot span the whole space. And the third one is S is a maximal linearly independent subset of V, that is if you add any vectors to this set, then linearly independent become then S become a linearly dependent set. The next is the pictorial representation of spanning set and linearly independent set. The first example is a very famous example for a linearly independent and spanning set. It covers all the rows and columns of a R power n, that is n by n matrix. And second example tells us a collection of vectors, and that vectors not spanning last rows of a vector space. Therefore, it's not a spanning set, but they are linearly independent. And third example is here, it spans whole space, but they are not linearly independent set. And last one example is here, not a spanning set as well as it's not a linearly independent set. Thank you all for your kind cooperation. I think e-content is very useful for you to learn about basis and dimension of a vector space. Thank you all.